All right, thank you very much. Okay, so welcome back to physics class. We are moving forward, getting closer to the end rather than beginning, so we're making progress here. Uh, Today, just as a reminder, today we're going to be doing another class on magnetic fields, in particular computing the strength of a magnetic field. On Monday, we saw how we could use the right-hand rule to get the direction. So today we're going to be doing some more quantitative problems where we compute the strength, and we're going to talk about the units of that and what they mean and so on and so forth. But before we start, I just want to remind you that there won't be a lecture on Friday. Instead, we will have the take-home exam, exam 3. This material won't be on the exam. The exam will cover basically weeks 10 and 11. So weeks 10 and 11 and the first class before spring break. So electric potential and potential energy, current, resistivity, resistance, capacitors, circuits, and the nervous system. So stuff from today and tomorrow will not be on this next exam. That being said, there will be a homework for today's problems. Since you'll have the take-home exam Friday, this homework won't be due Friday, it will be due Monday. So at the end of the day, Monday for today. That being said, if you have time, I suggest doing them as close to the end of the lecture as possible so the material is fresh. Also, please don't forget about the final or the second lab on capacitors. It's very quick. You can get it done pretty quickly, and I suggest trying to finish it before the exam. It's a nice review of capacitor properties. So any questions about that before we start new material? All right, hearing nothing, then I will assume no questions. So you can expect, I will post the exam tomorrow afternoon, and you'll have until, and you'll have 24 hours to get in your solutions. You can write out your solutions on loose leaf, take a photo, and you'll be able to submit on Canvas as the assignment. Like the assignment will have a file upload option, so that's how you will submit to me. It's not like official. The exam is not officially timed, so I'm not keeping a clock, but it will note if the exam is late on Canvas. So I'm going to give the due date 24 hours after it's posted. I'm hoping not to be not having to be very strict about that. I'm hoping it'll be quick. Everyone will get it in time. If you're like 5 to 10 minutes over, I'm not going to care. If it's several hours, then there will be a penalty. So it's not a hard time deadline because I know you guys have, it's not ideal testing conditions, and so I don't want to, but if it's like a day late, there will be a penalty. If it's 12 hours late, there might be something. If it's an hour or two, I'm not gonna care. Okay, so it's kind of timed is the answer there. Does that make sense? I'm trying to leave it open so people can work with their current situation. On the honor system, though, please don't try to abuse that. If you can get it in, please get it in. It's of course open book, open notes. You're welcome to look back at the slide videos and the slides. There's not really much of a better way to do it. Though that being said, I expect you guys to work alone on the exam. On the homework and labs, of course, it's okay to work together, but on the exam, please hand in your own solutions. Okay, any other questions about that before we start? All right, so going back to magnetic fields then. So Monday we talked about finding the direction of magnetic fields from straight wires and coils of wire. They're going to be our kind of model systems. Most of the problems that we'll come across can be modeled by those. Now we want to discuss how we find the strength of a magnetic field in terms of a number, and then express that as a vector. As far as magnetic fields go, they end up being something that you can't really analyze fully without calculus. So for this part of the course, I really just got to kind of give you some formulas that normally would be computed using integral calculus. We're not going to have to do that, but I'm just going to expect you to use the formulas. So normally I try to provide a lot of physical intuition into the formulas or as much as possible, but given it's a non-calculus based course, we're a little bit limited here with magnetism. So first thing let's go over some units first, and then I'm really going to have 4 formulas that we're going to use today in class. So the symbol we're going to use for the magnetic field is B, because M is already used for mass. So we're going to use B for the magnetic field. That's standard in physics. And the units of a magnetic field are named after Nikola Tesla, who was a physicist involved in using magnetism to generate alternating current electricity. So the units are named Tesla in honor of him, capital letter T. It's a big unit. So to give you kind of some ideas of what this unit means, it's basically meant to model the magnetic fields in large industrial electrical currents or near very strong rare earth magnets. So for instance, here you can look and see in this table that if you're really close to like a neodymium magnet, some magnetic material, and you measure its magnetic field, that magnetic field is about 1 Tesla. So that's kind of what this unit measures. Another example of something in that range is the magnetic field that's generated inside an MRI. So inside the coils of an MRI, it generates a field of around 1 Tesla. The fields generated in nature, for instance, from the magnetic field of the Earth near the surface is around 10 to the minus 5 Tesla. Or for instance, the magnetic field generated by, let's say, the current running through the wires inside your toaster oven, that's about 10 to the minus 6 Tesla. So regular everyday units are microteslas. But that being said, there are times where you can get units that or things that can generate magnetic fields that are quite big, on the order of 1 Tesla. So 1 Tesla is a really big magnetic field. But this is the SI unit. So we will stick with it. Most of the time in our problems, we'll be dealing with units of millitesla or microtesla, 10 to the minus 3 or 10 to the minus 6. So we're going to have really 3 or 4 here different systems for which we're interested in computing the magnetic field. Most of the problems we're going to get are going to be modeled as those. The first is the magnetic field from a straight wire. So what does that strength look like? How does it vary with distance from the wire? So here we have a wire with current, the wire's coming out of the page. So the wire is going in and out of the page, and the current is going into the page. So we're looking kind of at a top-down view of this wire with current going downwards. Using our right-hand rule, and I encourage you to check this as I talk at my screen here. But if you use the right-hand rule, you should be able to see that the magnetic field should point counterclockwise around the wire. The one thing we didn't talk about is how this strength varies, so that's really where the formulas today come in. It turns out from a straight wire and for most wires, the electric field got weaker, and we say as 1 over r squared. So if we remember, the electric field force had a 1 over r squared in it that determined it gets weaker. The magnetic field gets weaker as you move farther away from the current source, but it decreases more slowly. It actually decreases not like 1 over r squared, but 1 over r. So the magnetic field is inversely proportional to the distance. So there's no square. So in some sense, it makes the calculations a bit easier. So for instance, what this means is if you pick two distances here, so we could start at a distance here, this would be r naught at this distance. The magnetic field at that point is here. And then if we graph the magnetic field strength along this line, the strength being the length of the magnetic field vector, and proportional to how strong the magnetic force is, it would decrease like this. So here we're kind of graphing the length of these vectors here versus distance from the wire. So you could actually see it has this kind of, the graph has this kind of shape. It's a 1 over r graph, decreases a little bit more slowly than, for instance, an electric field from a charge. And you could kind of see this graph, if you just kind of graph the, try to connect the points of the vectors at any point around the wire, you could see this kind of graph repeating itself. At any direction around the wire, the magnetic field strength drops off like this. So this is the first formula you will need here. So the magnetic field from a straight wire. You might want to label this B, B sub straight wire or something, or just make a note of it. So copy down this formula. Anytime you get a straight wire in a problem and you need to compute its magnetic field, this formula will give you the strength. As for the direction it points, you still need to use the right-hand rule to get that. Oh, good question, Colleen. I is the electric current in the wire. So not intensity of the field, it's the electric current in this wire. So it's measured in amps. So B is proportional to the current, inversely proportional to how far you are away from the wire. Is that clear now? Okay, good question. So here, the other things in this formula, mu naught is a constant of proportionality. So it's a, again, something that has to be determined experimentally, and it depends on really the material that you're moving through. So what all of this space out here is. If it's air or vacuum, mu naught has this value. So the units work out to convert the current units and the meter units into magnetic field units. So this constant is these weird units of Tesla times meters per amp. So this number really, again, just think of it like an experimental constant. It's like the force constant K in Coulomb's law, or the big G force constant in Newton's law, universal law of gravity. So it has to be determined experimentally. And once we have done that, then we can use it wherever it appears in the formula. The 2 pi in the denominator comes from calculus, from solving an integral that I'm just going to state it has to be there. You're really interested in where it comes from, I'm happy to talk through. But otherwise, that's kind of will be outside the scope of this course. So to review, the magnetic field is proportional to the current and inversely proportional to the distance. All right, so that's case one, straight wire. Next, the other things we found were the other things we were looking at were several different versions of loops of wire. So a single loop and then stacked loops of wires. So let's look at the magnetic field from those things. We'll see it's still, the constants turn out to be a little bit different due to the calculus we're not showing, but the basic pattern of proportional to current and inversely proportional to distance still hold. So the next case here, we now have a loop of wire. So here we're looking at the loop of wire from the side. So it's like a ring and the ring is coming in and out of the page. So the current up here at the top is coming out towards us. It then loops around and goes back down into the page here. Often we'll have problems where we want to find the magnetic field right at the center of the loop. So right at this point here. And that point, the magnetic field at that point, the direction is again given by the right-hand rule like we talked about on Monday. And the strength of the magnetic field at that point is given by this formula. So here the only difference is now instead of the distance, lowercase r being in the denominator, capital R here is the radius of the wire loop. So make that note. Mu naught has the same value. I is the current in the loop. And the difference here is that in the other constants from the calculus is just that there's no pi in the denominator, just a 2. So that's formula number 2. Formula number 3 is really just a different version of this one. So maybe we don't have just one loop, but we have like 2 or 3, like we've wrapped a little coil or something, or we have several different loops of current stacked on top of each other. Maybe we want to find the total magnetic field from that stack right at the center. Well, in that case, all you got to do is take this formula here and multiply by the number of stacked loops you have. So that you'll see that that appears in the formula here. So this one in the bottom is formula 3. So this is for a small, what I would call a thin coil of wire. So something where you have, you could have any number of loops really, but they have to kind of all be really closely packed together. Okay. Examples and practice problems coming in a bit, but any questions on the symbols, the terminology, any of this so far? Okay, so the last system we're going to consider is also based on loops of wire. However, the next one is we want to know the field inside a very, what we would call maybe a thick coil of wire. So something where we have lots and lots of loops stacked on top of each other that are taking up, they have a not insignificant length. So that's the thing we called on Monday a solenoid. So it's where we have lots and lots of loops. And they take up some distance L. And if you get a lot of loops, the field inside eventually starts becoming constant and uniform. And it starts, the difference here is that once you have a lot of loops, the field you get inside really stops depending on the radius of the loops. All it depends on is the number of loops you have and the total length of the stack. So here, this would be the last formula for today, which is the magnetic field of a solenoid, or a very thick many-turn coil. So the main I think, confusion on the next set of problems. Really computing the magnetic field for our purposes in this class, getting the number in Teslas is, I think, the easier part of the problem. You just have to kind of figure out, based on the problem, which of these model systems is most closest to it and apply the formula. The hard part is really getting the direction of the field, or if they ask you for the direction of the current you need, because then you need to do the right-hand rule. So I think the harder part about, at least for our class, the magnetic field problems is the direction and using the right-hand rule. As long as you could determine, given your problem and the currents in your problem, which of these formulas apply, you generally just apply them straight away. And plug in numbers and chug and get an answer. You might have, for instance, a total magnetic field where you have a straight wire and a loop, and you have to compute both of their magnetic fields and then add or subtract them, depending on how they point. But that's about as complicated as it gets, and we'll do an example like that in a second. The one confusing thing that I think comes up a lot is, given a problem, should I use the thin coil formula or the thick coil solenoid formula that's here? And basically the way you have to decide that is based on the wording of the problem. More or less, if you're given the length of the coil stack, that only matters for the solenoid formula. So if you're given the length, or you're told how long this wrapped coil of wire is, chances are it means you use this formula, because you get this quantity, number of turns divided by L. So if they tell you how many turns of wire you have and the length, then you use the solenoid formula. If you're given the number of turns but you're not told how long the coil is, then that probably means they want you to model it as a short coil, in which case they'd have to give you the radius of the coil. So that's kind of key. If you're given that length here, then you're going to use the field of a solenoid. If you're not given the length, but instead you're given the radius in the problem, then you're going to use the thin coil formula. So that being said, this is our fourth and last formula for today. So are we ready for an example? Any questions before we move on? Okay, so our first problem is going to involve a thin coil. So we'll kind of look at that. So we're going to go back and make a note on the next problem. We're going to be using this formula, the magnetic field of a thin coil. So it's going to apply to one of these. Our textbook likes to give problems where we're using magnetic fields to confuse animals. So I'm picking an example like that and making it Washington College themed. So here, the goal here is to confuse turtles that use the Earth's magnetic field to navigate. As you may know, there are a lot of turtles that are able to sense the Earth's magnetic field, and they use the magnetic field to aid their migration patterns. Of course, we have a professor that likes to study turtles at Washington College, as we all know. So I've changed this problem so it involves Dr. Crockmall. So here we have I know these are probably not the turtles or the tortoises. I forget the exact species he studies, but I couldn't pass up this opportunity. So we have green turtles, and they are thought to navigate by using essentially the angle of the Earth's magnetic field. So going back to this picture of the Earth as a giant bar magnet, it has a magnetic field that's shaped like this. And basically the hypothesis is that turtles, as they navigate, can test their, can tell what latitude they're at by measuring, by actually sensing the vertical component of the magnetic field of the Earth, which is pretty cool when you think about it. So if the turtles are kind of swimming somewhere near the equator, the magnetic field near the equator is basically parallel to the Earth's surface, so there is no vertical component. However, if they're at some higher latitudes, let's say we had some ridiculous super turtle species that migrated all the way to the North Pole, they would see an almost vertical magnetic field. And basically by sensing that vertical component and how big it is, they could tell the latitude they're at. So we want to test that hypothesis. So to do that, basically we want to see if we can confuse the turtles. So Dr. Krochmal here is going to take a turtle and put a turtle in the tank. The tank is 72 centimeters in diameter, and what he's going to do is take a whole bunch of wire and wrap it 60 times around the outside of the tank. So then he takes a giant car battery or some kind of voltage source and runs a current through that wire and creates a, what he wants to do is create a magnetic field that perfectly cancels out the field from the Earth, or at least the vertical component of the field. The Earth's total field is 50 microteslas. And we're told at the location of the test, the Earth's field was 60 degrees below the horizontal. I'm going to give you a picture of this in a second, a real picture. However, I put together a very impressive cartoon of this situation. So model of this experiment, more or less this is what's happening. We have Krochmal putting a magnetic field on this turtle, trying to confuse it. So this is my non-scientific diagram. Take a look at it for a second, appreciate it, appreciate all the work that went into it. And then we'll get to the actual like useful diagram. I'll give you guys 5 seconds. I'm very proud of this. All right, moving on now, let's get a useful diagram. So here, I'm going to kind of speed up the vector mathematics here. So I will compute for you this vertical component of the Earth's field. So the total field is 50 microtesla. The vertical component is going to be that number multiplied by the sine of the angle of the field. So this vertical component that Dr. Krochmal is trying to cancel out is going to be 4.33 times 10 to the minus 5 Tesla, so 43 microtesla. In the northern hemisphere, the field points towards the ground, so we'll say that that's the negative direction, and we'll put on a negative sign there. So that's kind of where this negative sign comes from, and this one here. So drawing this problem, so the dark blue vector here is the total field, and the light blue vector is this component, 4.33 times 10 to the minus 5. That's the component we want to cancel, so we're going to put the turtle tank right in the center of this coil of wire. So here, this gray part, this is going to be a wire. This is a loop of wire. Really, there's 60 of them there, but I'm only going to draw one. They're all right on top of each other. So this is a loop of wire coming in and out of the page. So we're looking at the ring of wire kind of from the side. When Dr. Krochmal hooks up the battery and runs the current through the wire, what that means is that he generates a new magnetic field that points upward, equal and opposite strength to this vertical component here. Canceling out the vertical component, and whatever turtle is inside here should become super confused and be like, what's going on? Where'd my magnetic field go? So what this means mathematically is the field from the coil. So here we're not given a length, so we're not told how tall his stack of coil wires are. So that must mean we want to use the thin coil formula. So that means here, so what I'm going to have you guys do is take this away from here, solve for the current I we need in the coil. N here, remember, is the number of turns we have in the coil. R is the radius of the coil. If you need these numbers, I'll go back to the last slide, but they were in the problem statement. Just send me a message if you need me to go back and give you those numbers. The other thing I'm going to ask you guys to do, use the right-hand rule to figure out the direction of the current in this coil. Do we need the current to go in at the left and out at the right, or vice versa? So you have to think, using the right-hand rule, what direction of the current will give you this field? Does that make sense to everyone? Any questions, or do you need those numbers? I believe N was 60. Actually, let me just go back and get these numbers, and I will then come back to this slide. So N is 60, and the radius of the tank is 72 divided by 2. So we have the diameter of the tank. So N is 60, and the radius is 0.72 meters divided by 2, because we were given the diameter. All right, take it away, get me the current and its direction through the loop. I'll stop talking now and give you some time to work. Please ask questions if you have them. And once you have an answer for either of these things, please send it to me in the chat and I will let you know if you're right. So if you work through the numbers for this problem, as you guys got in chat, the current comes out to be about 0.4 amps. This is just the magnitude, not the direction. So to find the direction, you have to use the right-hand rule using this magnetic field here, circled in red. What direction does the current in this loop need to be going? Clockwise or counterclockwise, looking down from above, to create this field. So we're going to try that for a second, and then when you think you got an answer, feel free to post what you think it is in the chat and we'll compare. Okay, so we got 2 answers in the chat that are saying counterclockwise. So I'm going to put on the answer here and we'll talk through it. This, as you can see, the direction is the harder part of the problem. So what I'm going to see, so if we see the current has to come out of the loop on this side, into the loop on this side. So if we look down from above, so if we like look down from this direction, we would have to see the current going in over here, out over here. So counterclockwise is the correct answer. This is, again, the hardest thing about these problems are visualizing the situation in 3 dimensions. And of course, drawing it. So that's kind of the trickier part here. But hopefully everyone sees how the current has to be going counterclockwise. The way you can think about this is by doing the right-hand rule. So for instance, you can pick like a point on the wire. Let's just pick, let's pick this point. Take your right hand and put your thumb in the direction of the current. So that means your thumb is pointing out from the screen towards your face. And then you start curling your fingers to make like a fist, kind of like you're hitchhiking, and the thumb is pulling your thumb back to your face. As you curl your fingers, the direction of your fingers at any point gives you the direction of the magnetic field caused by this current. So our fingers would curl around this way. So we draw them curling our grotesquely long fingers until they reach this point, and at this point our fingers point up. So basically we have to do the right-hand rule in reverse here. So we want our fingers to curl upward at this point. And in order to do that, that means our thumb needs to point out of the page. So that means the current must be out of the page. That again is of course the trickier part of the problem, but that would be how you reason through it kind of in full. And then you could state clockwise or counterclockwise, or also if you had this diagram and you drew this dot and this X here, that would be also a complete full answer with the direction. Is everyone ready for a second example now? So one more problem for today and then we'll finish. All right. So here, before we move on though, just a brief intermission. So there's this nice, you can look at this, it's from a few years ago, but this Live Science article studying loggerhead turtle migration. So they attached all these electronic tracking systems to loggerhead turtle hatchlings, and then use that to check their swim paths as they migrated. And it was actually really cool. They determined how that the paths of the turtles swimming were basically always parallel to the lines of the Earth's magnetic field. It's a really cool experiment. It's also an exceptionally cute experiment, and I feel we need this picture of a cute turtle wearing overalls right now. So there we go. Let's take 2 to 3 seconds, look at this cute turtle wearing his overalls. And now time for another magnetic field problem. So this one's about an MRI. So MRI machines, basically what they do is they generate a really strong magnetic field that causes the spins of the protons and the hydrogen atoms in your body to precess and give off radiation. In order to do this and to set this up, you need a field of about 1 Tesla. It's a very large field, as we talked about. And basically, this giant, if you know what an MRI looks like or you've ever seen one, there's these big machines that have this big kind of round structure. The patient goes inside. This round structure here is a gigantic solenoid, like many, many loops of coiled wire, and they run a huge current through, about 100 amps, to generate this huge magnetic field. So here we're given, so we have a very long extended coil in space. So here they're telling us that the MRI is modeled as a solenoid. So we're going to use the long coil formula. And we have a few numbers here. So we know the magnetic field should be about 1 Tesla. And the length of the solenoid L is 1 meter. We're also given the diameter, but we're not going to need that. And we're given the current I as 100 amps. So take down these numbers. The magnetic field this is creating is 1 Tesla. The current it's using is 100 amps. And the length of the solenoid is 1 meter. So those are the numbers we need from the problem statement. Now, what we want to know is, to get this field of 1 Tesla, how many coils do we need? How many times do we have to wrap this wire around the patient? So how many coils of wire are inside this giant thing? So we can see here the picture over to the side, before we move on, is a picture of an MRI with the field on and a metal chair in the room, that the magnetic field inside actually gets quite strong and can pull metal objects into that procedure. So you have to be very careful with patients that have, for instance, pacemakers or metal plates in their body, or like screws in broken bones. The magnetic field can be quite strong and actually rip these things out of your body. Piercings are also a problem. So But our goal is going to be figure out how many coils of wire are inside this giant machine. So here we're going to use the coil formula, and our goal is to solve for n. If you want more practice, feel free to go ahead, try to solve for n, and that'll be our last problem here. Here we don't care about the direction. Since we're near the end of class here, what I'm going to do is I'm going to give you guys the number, and for those of you that need to go, you can feel free to head out now. That's our last problem for the day. You'll have the homework today has several options, several problems where you have solenoids, coils, and some straight wires. So there'll be more practice there. But if you want to hang out, work through your math just to make sure you get the right number, I'll hang out with you here. Remember, no lecture on Friday, but look out for that exam that's going to be posted. One note here is that depending on how your calculator rounds the permeability constant, n might not come out to be a full number. So you're just going to you have to have a full number of coils in the wire, so just round to the nearest whole number. If you round to one significant figure, this should come out to be around 8,000. But that'll be the end of our class for today, but I'll hang out for those of you who are still computing your answer and might have questions.